The language of logic. So this starts off with a whole heap of definitions. It starts off with the idea of a proposition. So a proposition is just a sentence proposing some idea, and that idea can either be true or false, but obviously can't be both. It can't be true and false at the same time. An example of that, it is raining, is a proposition. It could be true, it could be false, but it can't be both. As opposed to, is it raining? Well, that's not a proposition, that's a question. Now, logic, this idea of logic, it has its own language. Right? And it has an alphabet, but the alphabet consists of certain things, what we call propositional variables. It's a fancy way of saying pronumeral, probably. And so we might say, let X be the statement whatever, Y be the statement whatever. So whatever symbol we choose to use. So common ones you see is P for proposition, they might call it P1, P2 and so on. Q is another common one, capital X, capital Y, Greek letters. They're sort of common ones we see, but really it could be any pronumeral you like. Punctuation symbols. But in this alphabet, there's only two punctuation symbols. And that's the open parentheses and the closed parentheses. That's really the only punctuation symbols we have. And then we have our logical symbols, what we call the connectives, that join statements together. Some of these we've seen, some of these we've not. So the arrow going to the right is the implication symbol. And so that's often used in if-then statements. So if this happens, then this will happen. Now, there's two different ways you can do negation. There's this, well, what would you call it? A L that's sort of fallen over and gone backwards. But you know, that shape, which is probably the more common one, or the, I think they call those tildes. But anyway, that funny curvy thing. Right? And so that is the logical complement of a proposition. So equivalence is the double-sided arrow. So we're saying, hey, these two propositions are logically the same thing. Logically, they would be equivalent. And, so when we join two propositions, so the conjunction of them, both of these statements, and then or. Notice the similarity to set theory, the intersection we used use and an upside down use, very similar. So or is the disjunction of those two propositions. And then the quantifiers, which we did see last year in induction, type of proof. So the backwards E means there exists, and then that's, well, a V with a stroke across stands for all. And that's pretty much our alphabet. So a statement, what's a statement then? If I want to make a statement, it could simply be a proposition, or it might be a collection of propositions, which we've joined together with punctuation symbols, logical symbols and so on, but that's just what we call a statement. Now, a logically valid argument. This is what we're interested in. You have a list of propositions, and from that you draw a conclusion. Now, you've been doing that for quite some time because that is a proof. That's all a proof is, if you think about it. And that's why we've always been so fussy in the setting out of your deductive geometry, for instance, because what you're doing is forming a proof. You're writing a list of statements that hopefully connect to each other, and from that you can draw a conclusion. Now, this is not an example, this is defining example, okay? So an example is just a situation that demonstrates the assertion of a proposition. Why do I bother defining that? Because this one, the counterexample. And a counterexample demonstrates that a proposition is not true. It's often a lot easier to disprove a statement than to prove a statement, because all you've got to do is find one situation where it's false, and then you know your statement can't be true. And that's what we do. Find a counterexample. Find a situation where it's false. So yeah, we use that to invalidate the argument. Okay, so negation. Negation changes the truth value. So true to false, false to true. So if I let X be the statement, the number is even. The number is even. An example of that would be 6 would end up being a true, because 6 is even. Negation of X would then be its logical complement. Well, the complement of a number being even is the number is not even. Notice, the complement is not the number is odd. Okay, because there's more than just odd and even numbers. You have fractions, you have all sorts of things. So we're saying it's the complement, everything that's not even. In this case, now 6 would be false. So it's changed the value of that example. It's gone from true to false. All birds are black. So how would I write it? Well, there's lots of different ways you could write it, but remember, you're thinking of the logical complement. All birds are black are one situation. What could the other possible situation be? Well, at least one bird is not black would be one. As soon as I've got one that's not, I've got that. Another way you could say is, not all the birds are black. You could say it that way. Some birds are not black. So there's no one definite way of writing it, but it all has the same meaning. Using a bit of set notation here, our things. So let's have a look. Z is the statement. What on earth is all of that saying? It's saying there exists a real number. So X is an element of the real numbers. So there exists a real number such that its square is negative. Remember, it's just a statement. I'm not saying it's a true statement. It's simply a statement, which of course in this case, we know that one to be false. Well, the negation of that would be, and there it is in symbols, but that one means for all real numbers, their squares are greater than or equal to 0. And so with the notations, you'll notice I started off on the first one with there exists. Its negation turned out to be for all. And you'll see that a lot. If one is for all, its negation often involves there exists. Right? Because if you think about it, we're saying, well, for all, we're saying in every situation, so it's negation. Hang on, no, there exists one that doesn't satisfy that. Well, or opposed, in this case, I said, well, there exists a number, so its negation is no, all of them, for all of them, that can't happen. So what on earth does that mean? We're saying that the negation of X and Y, that's equivalent to saying I have the negation of X or the negation of Y. So that would be the same way of saying it. And a similar thing for the other way around. If the negation of I've got X or Y, that would be, no, I don't have X and I don't have Y. So they would be equivalent. All right. Implication. So they're our if-then statements, which is probably the heart of proofs. If-then statements. And for those of you that do any coding and computing, a lot of this logic is the basis of computing. Because a computer is a very logical machine, which does only have one of two outcomes. Because it's a binary machine, so it's 0 or 1. So a lot of this logic is applied in computer programming. So if-then statements. So P implies Q, that's what we're saying. That sort of statement. So if P is true, then Q must also be true. So in other words, P implies Q. P is what we call the premise of the implication. Q is the conclusion. P is a sufficient condition for Q. If I know I've got P, that's sufficient to say I've got Q. P implies Q. Whereas Q is a necessary condition for P. In order to have P, I must have Q, because if P implies I've got Q, if I don't have Q, then I don't have P. So it's necessary condition. Here we go for an example. Statement X. You receive a band E4 for extension 2. Well done. Statement Y, you score 90% or above in extension 2. Well, X implies Y. If you get your results and you got a band E4, then that implies you must have scored 90% or above. So receiving E4 is sufficient to conclude that you got 90% or above. Whereas scoring 90 or above is necessary to receive the E4. Because you get the mark first, then the mark gets turned into the band. So there's our example. In reality, they're probably equivalent statements. Converse. If you want to find the converse, it's basically reading the theorem in reverse. So reverse the implication. So the converse of P implies Q is Q implies P. The converse of a true statement may or may not be true. It's not necessarily going to be true. And similarly, the converse of a false statement may or may not be false. Here we go. X, it is raining. Y, the grass is wet. So it might be true that X implies Y. So it might be true that because I know it's raining, I can conclude the grass is wet. But it's not necessarily true that Y implies X. I mean, the grass may be wet, but it does not necessarily mean that it's raining. Equivalence. These are our if and only if statements. You may recall last year I wrote IFF down. I think it was slopes were parallel if and only if, or lines were parallel if and only if. And you all thought I spelt if wrong, but I hadn't, right? Because it's an if and only if statement. And they're ones that do read backwards. P implies Q and Q implies P. So if each is the consequence of the other is another way of saying it. Now my example here is X is the statement, ABCD is a parallelogram. Y is the statement, diagonals AC and BD bisect. Well, X implies Y, that's certainly true. That if I know ABCD is a parallelogram, yes, I can conclude that the diagonals bisect. And Y also implies X. If the fact that I know is that the diagonals bisect, well, that's enough to say the shape is a parallelogram. So it reads both ways. X is equivalent to Y, and so the way we really should write that theorem is ABCD is a parallelogram if and only if the diagonals bisect each other. Don't know if you would have heard of this one before. Contrapositive. The contrapositive of an implication is when you negate the converse. So if the original statement is P implies Q, the contrapositive statement is not Q implies not P. Why is that useful? Because if you can prove the contrapositive, then you can conclude the original statement. Sometimes it's easier to prove the contrapositive than the actual statement you're trying to prove. So P implies Q is equivalent to not Q implies not P. They are the same thing. They are logically equivalent. So here's an example of that. A polygon's a triangle is one statement. The interior angle sum is 180 degrees. So X does imply Y. If a polygon is a triangle, then the interior angle sum is 180 degrees. We know that. Not Y. If the interior angle sum is not 180 degrees, then we can conclude that the polygon is not a triangle. So it's the same thing. So X implies Y is equivalent to not Y implies not X. This last bit here on truth tables. Truth tables are definitely not in the syllabus. I want to make that clear before I start using these. But I do not understand how you can look at this idea of logic without considering them. So I'm going to put them in there just so in the next few lessons I can actually prove some of the methods of proof that we're going to use. So that you don't have to do that, but let's see if you get hold of this idea of what a truth table is. So here's my table. P's a statement, Q's a statement, then all the possibilities of our symbols there. I could have not P. I didn't bother putting not Q down, but not P. I could have P and Q. I could have P or Q. I might have P implies Q, and I might have P as equivalent to Q. You'll notice there's 4 lines there. Because of our statements, there's 4 possibilities or permutations, if you like. Okay? Now, to try and get our head around this, I decided the statements we'd use is P is the cat is white, Q is the dog is black. Okay. Now, both of those statements could be true. Now, if that's the case, not P, remember, changes the truth value, so it must be false. P and Q. Well, if they're both true, then that is true, that both the cat is white and the dog is black. P or Q, well, that would be true as well. The cat is white or the dog is black. Oh yeah, that's true. P implies Q. If the cat is white, then the dog is black. Well, the fact that the cat is white is true and the dog is black is true, so perhaps I've got a true statement there. And P is equivalent to Q, well, they're both true, so yes, those statements are equivalent. But I could have where the cat is white but the dog is not black. Not P would become false. P and Q would now be false, because it's not true, both those statements now. P or Q would still be true, because one of those statements is true. P implies Q would be false, because I've got the cat is white, but it ended up that the dog was not black, and they are not equivalent statements anymore, because one's true and one's false. If we reverse it, where P is false and Q is true, so not P obviously becomes true, P and Q, again, will be false, but P or Q would still be true. It's the implication one. And this is the one sometimes people can't get their head around. It's now a true statement, even though P is false. Why is that? Well, it's okay. I could have Q end up being, the dog is still black. Like, P might imply Q, but that doesn't mean you can't have Q without P. All we know is that if I have P, then I have Q. But it is possible to have Q in other situations. So it's possible to still have a true statement when P is false and Q is true. And equivalents, well, no, they're not equivalent anymore. Well, what about if they're both false? Okay, not P is true. P and Q would now be false. We don't have both situations. P or Q is also false. P implies Q is now true. And P is now equivalent to Q because they're both false. So when I was doing my logic, all I remembered was things like this. Well, hang on, P and Q, the only time it's going to be true is when both of them are true. P or Q, the only time it's false, is when both of them are false. P implies Q, the only time it's false is when we have true false. And then P equivalent to Q, well, if they're the same, we end up with true. If they're different, we end up with false. Let's see if you can now do this problem. Whether you want to use truth tables or whether you want to just use your own logic, you'll notice I have not put the answers on the sheet this time. So you're going to have to work it out. So there's Alfred, Kurt and Rudolph. They're accused of stealing and selling copies of an exam. At the inquiry, they testify as follows. Alfred says, Kurt is guilty and Rudolph is innocent. Kurt says, well, if Alfred is guilty, then so is Rudolph. And Rudolph says, I'm innocent, but at least one of the others is guilty. So the questions, can everyone be telling the truth? If everyone is innocent, who lied? Assuming everyone's testimony is true, who ends up being guilty? And if all the innocent tell the truth and the guilty lie, who ends up being guilty? Let's give you a little bit of time to think about that one. So my three statements, for convenience, I'll call them A, K and R, and simply that I'm going to make a statement that each one of them is guilty. So Alfred's guilty, Kurt's guilty, Rudolph is guilty. All right, here comes my truth table. There are a lot of permutations here. Starting with true, 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 going all the way down to false, false, false. All right, let's start with Alfred. Alfred said Kurt is guilty and Rudolph was not guilty. So I've symbolised that as K and not R. K, so fill in the K, not R, so we change the value on all the not R's. Now what did we say for and? They're all false except for true and true. So we know those ones will be true, the rest must be false. Now let's have a look at Kurt. Kurt simply said, if Alfred is guilty, Rudolph's not guilty or something like that, wasn't it? So A implies R. So let's fill in A and R. Now A implies R was always true except when true led to false. So those two would be false, the rest would all be true. Now comes the more interesting one, Rudolph. There we go. He said, I'm innocent. So not R and one of the others. So the other situation is A or K is guilty. So let's fill them in. So not R, we'll change the values on all the R. There's the values for A, there's the values for K. Now we work like parentheses inside out. First of all, I'm going to have a look at A or K. The false false will be false, the rest will be true. So now it's like I'm saying, well, this first row, the not R, with the ones I put in blue. And we're saying we have not R and that value. So those three will be true, the rest will be false. So now let's have a look at those questions. Can everyone be telling the truth? So we're now looking at a situation where, there it is, right there. So yes, if Alfred was our statement, not Alfred's statement, but the one we made about him, if he is innocent, Kurt is guilty, and Rudolph is innocent, then all statements would be true. So yes, it is possible. If everyone is innocent, which means, I'm looking at the row that's false, false, false. Who lied? So who came up with a false statement? Well, both Alfred and Rudolph came up with false statements. Assuming everyone's testimony is true. So now we're saying everyone's testimony is true. So I'm looking for a row that has 3 red T's. And there it is there. Kurt is the guilty one. Kurt is the guilty one. If the you got to really look at it hard for this one. If the innocent tell the truth and the guilty lie, the row we're looking for is there. What? Right? The innocent tell the truth. Right? Now that's this one here. So Kurt is telling a true statement and he is innocent. The guilty ones lie. So it's true that these two are guilty, they lie. We'll have a go at 2A, which is having a look at the different terminologies and things like that.